technical issues. There was kind of a demo planned, but I can't plug the display for some reason. So today I'm going to talk about modeling the OSGi way, or modest modular models. So like others, I've been trying to improve my code, and like many developers, I'm very lazy. I don't like to write the same code over and over again, even twice. So I like to make my code reusable, understandable, and also maybe maintainable. That's really the word I'm trying to find. So in the past, I've been an Eclipse developer, and I've used the Eclipse modeling framework. And it kind of had the premise that you would be able to reuse your IDs, and maybe if you changed language or something, you could reuse the same IDs and not just the code. But when I was an Eclipse developer, I was more attracted by OSGi. I became an OSGi developer. And it had kind of the same promise that you would be able to reuse and maintain your code. But after many years of being an OSGi developer, it achieved that. I can reuse and maintain the code, but the IDs are kind of trapped within my Java code. At the same time, for a long while, I've been a functional programmer, and I'm following what's happening in the Haskell community, in the Clojure community, which are like different ends of the spectrum in terms of functional programming, from static to dynamic types. And so recently, I had this idea in my head to try to mix modeling, modularity as in OSGi, and some modern practices from the functional programming ecosystem and the way that they do things. And today I'm going to talk about the results of that experiment. It's an exploration. It's a prototype of a new modeling framework that has a new take on modeling as well. And it's not ready to use for production. It is a prototype. It will be available as open source eventually if I finish it. And I want to talk about the insight I gained during that journey. Okay, so first, I know that there is not a lot of overlap between the Eclipse modeling communities and the OSGi developer community. These are like two schools of thoughts, and it doesn't mix so well right now. So I'd like to know if everyone here is, has used EMF, for instance. Can you? Yeah, so lots of users of EMF, but not everyone. So I have to go through a quick intro of what modeling is, so that everyone gets up to the point where I can talk about what's different with my approach. So as I said, I left Eclipse development, and I'm like regular Java OSGi developer. And on a project I was working on, it was a very common picture of a project. You have this Java backend, you have an Angular front end, and you use REST to communicate. I was the architect for that project. We are doing everything by the book, best practices on both ends, technical practices at least. But we had some problems, like because of different schedules, because we didn't have so much time to synchronize. The front end and the back end, which were using the same data types, the same services, started to drift away. And sometimes you had the same abstraction with different structures, like or sometimes the same structure with different names. Sometimes, we didn't know which one was right. And if we wanted to change or fix things, we would break things, and it would become difficult to maintain. And we had that, and we duplicated the effort in the first place to think of how things should be modeled each way. Basically, they saw the JSON, they say, okay, let's reverse engineer this, and we didn't have a lot of talk. So we could have had more talk. Like, we had the best practices for technical side, but not on the process. I'm sure process could help, but I'm not a big fan of process if I can have a tool that does it for me, and that would be great. So the idea that is not a novel idea is how would it be if we put our models, like the types, services, APIs that are shared in a separate repository that is Not just for documentation, that would be great because we don't know which one is right. So right now, documentation would be great, but also as a source of truth, as a computer artifact, like software artifact that we can work with. So that's kind of the idea. So here we would have the model. We would put our data types, our services. I'm not describing precisely in which shape it would be. And we would generate, synchronize. Let's not go into details right now. The backend source code. So here there is a Java data types that correspond to those model data types. We have them here in TypeScript. We have the same for services interfaces. We're doing OSGi, and we can do also component-based design in TypeScript with Angular or other frameworks. I could also generate the stubs for the DS components. That would be scaffolding. It would be quite practical when I start to design an application. Could go fast. The mocks for the test, and I could go on and on like that. So that was the plan, and it's not a bad plan because that's what jhipster does. It's quite a famous project. It scaffolds your Spring Boot plus Angular application, and it's quite successful as a project. But it's just one instance of a bigger picture, which is modeling. It's a problem that has been treated by EMF, and it was for me an excuse to get back to that personal pet peeve, that idea that I had in my head to work on modeling with a different approach. Also, it's a perfect example for this talk because modeling is quite abstract. So I will be using this example, this use case throughout the talk to explain what I'm doing. So I wanted to start on modeling, do something maybe like OMF, but with modularity and modern practices, like in functional programming, in mind. So what's a model? So this is a fun slide, but I find the etymology of this word fascinating because it comes from modulus and modus, from Latin, which mean way, mode, or measure. And it's a cousin of a more recent term, module. So we are doing all the time Java modules in OSGi, and these words are similar because they're actually cousins. And it turns out that modest is also a cousin. It means measured, well measured. So that's the subtitle of the talk, modest modular models, like the same word drifted with slightly different semantics, and that's a good fit for what we're trying to solve. But this day we use the word model for a definition, a presentation, or an abstraction. So models are actually everywhere, or everything, the way you look at them. So if you have APIs, your APIs, you're modeling something, you're expressing something. The schemas, obviously, the programming languages are a collection of connected models. Like you have the AST, you have your type system, maybe you have your Java memory model. In machine learning, they talk about models, which is how they plug their networks together. OSGi, obviously, is a component like Java modularity model with a service model, like a bunch of models that go together. So basically, we all do modeling all the time. But we do it on the whiteboard, we do it in our head, on paper. And the difference with model-driven development is that model-driven development makes the models first-class citizens. It's like when you add types, if you write some assembly code, there are no explicit types, but you have it in your head. If you don't know that this is a float or an int or anything, you can't work that out. So whether the type is known as static time, whether it's explicit, it's a detail, let's say. But models exist, and modeling is like going to typed languages. You say, okay, now my API is going to be reified. This is going to exist, and I'm going to be able to work with what an API is, what a part of the programming language is, what a database schema is, and you're going to have them as objects. Like, it's a bit like in Java when you have jars, and they're just some passive artifacts, but you make them bundles, and then they become something you can install and remove. So model-driven development is thinking about models and their relationships. And I'd like to go back to the example to go further. So this is exactly the same side as before, so just we have it in mind. We generated the backend source code and the front-end source code, and maybe other stuff, like the Swigger API. We had Swigger API like the 3 first months of our project, then we were lazy to update it, because things change all the time. And now, there's a new spec in the Linux Foundation. It's called OpenAPI. It's just like Swagger, but standardized. And we have to rewrite it. If we had models, we just could say, OK, let's generate that as well. OK. So in that sample, I separated the model repository. But once again, modeling is not about where the data is located. It's not about how it's represented. It's about the abstract data, what you want to fill in, what these data types are. It's like you can represent them as Java classes, you can have them as annotations, you can define custom languages, you can have them as JSON or XML. The model is the data in memory. It's like you take a programming, or not even a programming language, a declarative language, and you remove the syntax and say, OK, the syntax, this is just a way to create instances, but I could write them with Java and write new object, whatever. And what matters in the model is what's the structure of things. So having a separate repository, so just we could have generated a TypeScript from Java, like find the Java code and think this, let's generate the TypeScript definitions that are equivalent. But it doesn't matter, it's still modeling. You still go back to your model, abstraction model, then you go back to TypeScript. A separate repository is useful if you want a neutral language. And these languages, like domain-specific languages, are tailored to express exactly what you need. And through that, you can also enforce good practices. It's also something we can show to someone who is not a programmer. When we show Java to your customer that is not a computer scientist or software developer, it's a lot of gibberish for him because there's a lot of extra information. Well, if you have only a mathematical definition, if he has some science training, it's OK. So basically, in domain specificity, it's modularity for models. Domain-specific languages, modularity for languages. Instead of having one big general-purpose language that has all the constructs, you modularize it in several models with the constructs orchestrated differently. And it has several advantages. So it's the complex versus simple axis. So if you have fewer constructs, your instance are going to be smaller in terms of what they can do. So you can maybe translate, when you update the model, you can translate your instance and say, OK, I've made a backwards incompatible change. But look, now I know there are so few constructs that I know how to update you. So imagine that if Java came in a new version and changed the backwards compatibility, they could say, OK, your code is broken, but we can update it and prove that the new code is going to run just fine. That's very good property. It's the same with OSGi, like monolith versus modular. So your modules are easier to reason with, but the interactions between them are going to be more complex. So we find the same problems as with modularity, but it's not, at the end of the day, so far, DSMs and general purpose can coexist. That's a typo. And it's just a way to go to that road, but you don't have to go the whole way at first, right? So I'd like to talk now about a bit more the fundamentals of modeling. This was a bit on the surface. So in modeling, we talk about models and meta-models. So just before I was describing my service in my model in a certain service model that was able to express services. It was its job, and I wanted to describe my service interfaces. Well, that service model itself is defined in another model. So for my service, my meta model was the service model. And the service model has another model, the meta model. So that looks like that. This is a zoom on the model that I had before in my separate repository. I had my data types, I had my service definitions, and they are expressed in the service definition model. My data types, they are defined in the data type definition model. And it turns out, so my services could use my data types, obviously. It turns out that my service definition model, it's itself defined as a data type definition model. That's a property that we find in all modeling frameworks. And the data type definition model defines itself. It's able to define itself. So it's a special model, and it's called sometimes MOF, the Meta Object Facility, or if you use the EMF, this special model is called eCore. So it can be used to define all the structures, because it's a structural model, but you can't define the semantics there. They have to be defined elsewhere, and that elsewhere is in a transformation. So basically, it's like a function that takes a bunch of models and outputs a new model. Like, for instance, if I had my service definitions, which were of metamodel service, it's like a variable in its type. I want to have Java interfaces, which are also like instances of a higher level metamodel, which is called Java model, which represents what Java is. Then I could ask, serialize that as Java. So a picture is 1,000 words, so this is a big picture, so it's a lot of words. This is what we had just now, like this part is what we had just now. But I added the rest. So it turns out that the data types and services, we have to put them in a way in memory. And we can use a textual representation, like source files for that. So these files, like the service definition, are passed by a service providing textual grammar for these files that is able to take, let's say, a byte stream and create a service definition model in memory. And the same goes with data types. Once I have these in memory, I can transform into the Java model. It's like a function that takes a data structure and transform it into another data structure. It's like a converter. And these turns out that the Java model and the TypeScript model are also defined by the data type definition model. So everything is connected. And then I can serialize them as Java code or TypeScript code. I could go the other way if I have a parser. So this is interesting, but it grows fast, very easily, very fast. It's very nice because if someone else provides another domain-specific model, maybe for a special kind of business line, and then they want to express something in a nice format, they can transform to these, not go directly to Java, but go to data types, go to service models, and then use the whole pipeline to go wherever they want to go. But because it grows fast, we kind of need something to handle all of that, and make it work together. And that's the purpose of a modeling framework. So it's kind of a middleware to define models, to refer to them in a consistent way, to provide transforms between models. Say, oh, I'm able to transform this from that. So now anyone can use that. We can see if we are OSGi developers that this looks really like a service. We can hook serializer. When I'm talking about serializers, it can be through the network, but it can be serializing a model as Java code. So you can have several dialects as well for one language. And there's a strong network effect when a middleware is used by the community. They had other models, like someone had some, I don't know, persistence for some framework, and then you have this Java model, and everything is going to be hooked together. And basically, you get the same kind of integration that you get with OSGi, but at the model level. So it makes sense to have a framework. And it's also interesting sometimes to have what we can call meta reflection. Is if I transferred my service definition into Java code, if I use Java reflection, I'm going to see the results of the transformation. But the original intent from the model that I had is potentially lost. So maybe I can ask the framework, oh, by the way, can you give me information of how this thing was in the first place, so I can have a higher level overview of how things are, and maybe have a diagram. Like it's difficult to have a diagram from Java code, but maybe it's easy to have a diagram for a domain-specific model. So obviously, if we're talking about frameworks, There is the elephant in the room, the Eclipse modeling framework that I talked in the beginning. It's a major free open source software. It's a huge ecosystem, and a lot in EMF resolves around eCore, which is like the core building block that I talked about. It generates Java models, Java code, which are Java beans on steroids, which are hooked into a runtime part of eCore, of EMF. And then everything hooks into that, if you've used it, like data binding, persistence transaction, and everything using Eclipse plugins or OSGi bundles, if you like. So why do people use EMF? They scaffold the application fast. There is an extremely rich ecosystem. It integrates really well with Eclipse. And they have solutions for everything, and including diagramming and parsing and so on. So why not EMF? Well, because these are Java beans on steroids, and Java beans were the hip thing 15 years ago, but now a lot of people have moved away from Java beans and moved to immutable data types. They fit really well the microservice pattern, where we want to have everything as DTOs, basically. They are concurrency friendly, so you can run any thread as you like on them. You don't need locks. You can remote as you like. And they have very nice properties. So, also, in EMF, you depend on the object. So you draw a dependency. And if you're a Java user that is not in Eclipse, that's a new dependency. That's a pretty strong, hard dependency to take. And most Java projects won't use it. And then there are the problems with EMF itself, which is built around the old infrastructure in Eclipse. And we can't really fix EMF like that. It's 15 years old. People have tried, but any significant change would break everything. And so there is no easy way out. So let's start something new. And my experiments, I called it Praxis. It's for a modular modeling framework. So I said the modular way because it's built with modularity in mind, the OSGi way, because OSGi is built really in a modular way that you don't even need OSGi. Like when they do the DS spec, they find a way that you're going to use your components without requiring DS or OSGi. That's how modular you want to be. And that's what I'm trying to achieve with Praxis. If I want to generate some equivalent of a bean, like the data object, I don't want to force anyone to use Praxis if they don't want to. Okay? So I'm using itself like component-based design as in OSGi. It's fun because it's building itself. Like the code is itself the output of the previous version every time. And it draws ideas not only from EMF and OSGi, but also from Clojure, Haskell, and a bunch of other communities. And as I said, you have EMF with eCore. Every time you have this first data brick, which is the center of your platform. In Praxis, it's called Plato data, and it's a persistent data model. And when I mean persistent, I mean like as in functional programming. It's not about database, it's not about storing things. It's about having immutability, and when you make a change, you return a new version, and only the diff has changed. Like you have lots of overlap in memory, you don't need to copy. It also provides things we like in Java, like, or in programming in general, so algebraic data types. So you can have pattern matching, you can have builders. And when all of these objects, when you generate these models and they all share the same data structure, the same superstructure, and the same properties, like non-nullability and so on, it becomes really easy to work. You have a lot less cognitive overhead because you know you don't need to care about this or that. Like if you got a pointer from a CLib, you don't know if you need to clean it to free the memory if you don't go to the documentation. If you get a GC, then you know you don't have to care. Well, it's the same. When you get no nullability, you don't have to do null checks. When you get no mutability, you don't have to have locks. You don't have to care or be scared that someone else, some user, is going to destroy your application because it's mutating something or passing a pointer it shouldn't. So yeah, you get concurrency and remoting friendliness. You don't have, as I said, external dependencies. And if I want to say like have meta reflection, it's going to be through an OSGi service. Everything is going to go on layers on top that you don't actually need, but if you want to use it, obviously, you have to use it. So now I'd like to show a bit how we can model application this way, like real OSGi applications. So OSGi is like service component architecture within the JVM. Okay, service contracts that are provided and required by components, bundles to package everything together. And right now in practice, we have this Plato data model that allows us to write data models in Java or maybe in other languages. So I can define new models. So the service model that I talked to before is called Plato service, and there is a Plato component model. And the idea is to support the methodology of writing up OSGi applications through languages and through models. So instead of going to Java and being like, oh, I have all these constructs, so what do I do now? I need experience, I need some ID. This is supported, the workflow is supported by the language and maybe the tooling around it. So I'd like to just build a simple application. Let's say I have this service. It's to-do manager. I can add, remove, or list a to-do. I have an implementation. I have a controller. So these are components. This to-do itself is a data type. So how do I go and build it? Well, I first define what to-do is. So I can define it that way. I say type to-do has a title, which is a string. Author, this is a string. Contents refers to another type that is defined here. You see you have union types. I don't know if you can see, but I don't think I can zoom. I mean, I'm not a Mac user. Okay, like this. All right. So you can have union types. I'm saying that the to-do contents is a simple to-do contents or a composite to-do contents. It refers to other types just here. You have enums like color is green, red, blue, or orange, and so on. Okay, this is just a sample. And I can have imports. Like I can import code, a type from Java, and I have this magical Java model because I don't have time to build an abstraction for every API that under the world. If I wanted to use it for TypeScript and for Java, I have to like create this timing model that is platform agnostic. But if I want to take a shortcut, I can say, okay, take me from Java time, and then I'm going to use it. All right. And then I can define a service. And as same goes, I can just import from the to-do model that I just have, the data model. I can import it completely as to-do and refer to the to-do type. And I can obviously refer to some Java types like the OSGi promise and the reactive stream publisher and say, okay, this is going to be an async or reactive service because I'm providing promises when something is done. So now is the time for the demo. But turns out the demo is on that PC, which is a bit disappointing, but I think we'll have to skip it. I wanted to show the way we can, how the Java code looks. So it's not generated to be ugly. It's code that should not be modified by hand. We can have static checks and break the build if someone does it. But it's also code that is like code we would write if we were not lazy. It's not code calling to the framework. It's very simple. And I have also the TypeScript code for that. So it gives me some time to talk about the next things that I want to follow. So if I want to talk about what's next with data models, like if I want to match EMF, I have to solve what EMF is solving, and they're solving big models. Think I have this to do, but I have hundreds of thousands of to do. It won't fit in memory, or billions of to dos because they're pretty small. So I want to put them in a database it can fit outside of the memory. So I don't want to pull everything, right? I want to be able to pull parts of them. But since we have models, we can not only generate the Java code for the persistent model, but we can generate something else. We can actually generate services and components as well for that to provide something that is ORM-like, that is like well-typed, but provides reactive. So I don't know if you know about reactive, but basically it means non-blocking, back pressure aware access to this data and say, okay, I'm going to pull 1,000 of data bytes of gigabytes of data, but I'm not going to fill my memory. I can take parts of them. So the big idea of this slide is that when you have a modeling infrastructure, you don't have to always think the way we used to think and say, okay, I'm going to generate Java now. No, you're going to generate to another model which has already the infrastructure to generate Java. And these models are very simple to transform to because they have few constructs. If I want to generate a service interface or a component, it's very easy because it's only a bunch of lines, but I get all the benefits from hooking into that infrastructure. Another thing that is interesting, I believe, is how we can layer models on top of each other. If we can reference where an element is, I would like, for instance, when I'm reading the source file just now of my type definition, if what it does is that it generates an instance in Java of those classes, but they don't have any information about where the lines are, where they don't know about source anymore. They've gone into the modeling world, but we need to sometimes, if we want nice errors, to know where it comes from. So I would like to tag elements and like put another model on top. I call that, layered models. And that's something I want to build. And when we have that, we can enrich models. And like, for instance, if I wanted to have REST endpoints on top of my service model, I don't want all my services to have REST endpoints. I could customize them with a specific model and say, look at this service interface and look at these methods. I want to expose them on those paths with those mapping schema or something. All right, so I think I'm done. So about this experiment, so it's still an ongoing project, but what I learned using it and mostly rebuilding the framework with itself is the comfort and the peace of mind we get from having persistent models and the way it makes everything simple. And especially when you do transformations and you're going from a persistent model to another persistent model, it's very simple. And that's what Clojure developers say, because they use that all the day and they say it's a big thing. And yes, it is a big thing. So most of us, we are in certain community and we have these echo chambers like within OSGi, within modeling. And it's nice to see outside what people are saying and actually they were saying, this is great. Yes, this is great. This is an insight that I gained. So I'm also very interested in the borderline between static and dynamic. And OSGi is right in the middle. It's like trying to bridge static types and dynamic types. While modeling is the same, at the same place, but in an abstraction layer above it. And finally, last point, it can support methods and tools, and they shape the way you think. Like, it's hard to get people to use OSGi, right? But if you had, and we're talking all the time about tooling, well, if we had this, like an editor that says, okay, this is the way you write OSGi, and if it's not the right way, it doesn't compile, and you get nice compilation. That's what the Xtext guys are doing as well, right? It will shape you and make you, it will make it easier for the users. And we can also hook a lot of things on top of that. So I'm done. I don't think there is much time for questions. If I
1 or 2 questions at most.
And just I want to say that the URL is, as I said, it's not published yet. It's where it's going to be. So when someone puts it on SlideShare and they click it in a few months, it will not give a 404. But I will announce it on Twitter whenever it's ready. So if you want to follow me, that's also a way to keep tuned. So thank you very much. And if you, one question.